Welcome back to a jam-packed review here. This is Big Idea B. We're going to go through B1, B2, and B3. And so hold on to your butts because we're going to be going fast. So we're going to start off with question A1. What's a fossil? How do they form? What do they tell us about the history of our planet? So if we take a look at fossils, it all comes down to the basics, just like dodgeball, you know? And the basics of becoming a fossil are real simple. Couple things have to happen. First of all, understanding a fossil is the remains of a once living organism, a once living thing. So you've got 5 steps when it comes to fossilization. Step 1, the critter's got to croak. Okay, so an animal will end up dying, and that's the first step in becoming a fossil. Step 2, you're going to need to decompose. The soft parts need to be eaten up and used up by bacteria and other animals. So decomposition is part of a normal process of life and death. Along with decomposition, you're going to need a rapid burial. In order to become a fossil, the bones or the shells need to get buried fairly quickly so they don't become, chewed on, broken up, and strewn all about the place. So a quick burial is a good way to becoming a fossil. If the animal stays out too long, the pieces are just going to get scavenged and destroyed. Now, here's the interesting part. In step 4, the fossil needs to, or the wannabe fossil needs to be chemically changed into stone. This happens with water in between the pore spaces, buried down deep in there with it. And the water can help this chemical process happen, where the atoms of carbon are plucked out and silicon are put in its place, and it slowly converts into stone. So that when you actually pull the rock out again, when you pull the fossil out, it's not real wood, it's not real bone, it's not real shell. It's been turned into quartz or pyrite or hematite or things like that. Then, of course, the 5th and most important piece is you need to finally expose yourself to the surface. Fossils are no good if they're buried underground, and so having them on the surface is the important thing. So remember the 5 steps here to achieving fossil-lictory here. You need to die, decompose, rapid burial, turned into stone, and then exposed to the surface again. Now, knowing that, there are lots of different ways that things are fossilized. Of course, the old traditional would be altering hard parts, taking something that gets buried and turning it into stone. So shells, a great example of things that are easy to fossilize. Wood is another one because wood tends to decompose very slowly, so it sits out for a long time, and so it's a good candidate for being fossilized. Bones, another great candidate. And teeth are another good possibility, like shark's teeth, for example, in this picture right here. You can also mummify a creature if it gets buried in ice and its body dries out, like in this mummified baby woolly mammoth that you see right here. It's also possible, as in the case of the woolly mammoth, the DNA is still intact. It's also possible here that you could preserve animals in amber, insects mostly. And amber is just tree sap. And the tree sap captured, rolled over this insect and trapped it and then hardened into amber. Now, just like with the mummified remains, this is original organic material. These have not been altered into stone. So it's intriguing. Could you get DNA out of them? So it turns out if it's something in the case like here, if the DNA is really old, more than 100,000 or 200,000 years old, usually the DNA falls apart at that point. So it's not quite like Jurassic Park where you can extract blood from a mosquito out of amber and be able to recreate a dinosaur, but it's still kind of cool. Now there are things called trace fossils, or they're wannabe fossils, things that look like fossils but they're not the actual critter. One example would be worm burrows. You know, if a worm burrows down and creates a hole, a tunnel for itself in the sand. I'm thinking out in the middle of the ocean, marine worms. When that creature dies, the hole could be preserved. That's what worm burrows are. Footprints are another great example of a trace fossil, something that's not really a fossil but being preserved. Trails are another one, kind of like footprints. Trails are just like that, where it's the remains of not the organism, but certainly evidence that the organism was there. And of course, the most famous one would be coprolites, or AKA fossilized doo-doo. And it is rare, but it can happen, and lots of interesting things can be learned from it, like the diet and the behavior of the animal that you're finding and dissecting their coprolites. So, lots of things to learn from fossils. That's A1. Now, A2 is going to be a series of several prezzies here They don't take long, but they're important. We did a series of labs where we tried to discover and learn what are the different parts of fossil or of rocks. So we found out a lot about igneous rocks, and one of the important things are these 5 laws right here. Igneous rocks come from lava, that's melted rock, and that cools and crystallizes and freezes into solid rock. Igneous rocks can form on the surface or deep in the ground. Igneous rocks that form on the surface cool fast and have relatively small crystals. Igneous rocks that cool deep inside the earth can cool much more slowly, and they have a long time to grow large crystals. So crystal size tells us a lot about location and rate of cooling. And we even have igneous rocks with air bubbles in them, and those froze so fast that the air bubbles were trapped in with it. There's some important vocab words that go along with this. Of course, you have coarse-grained, which are igneous rocks with huge crystals big enough to see with your own eye, like in this diagram right there. You can also have the opposite of coarse-grained, which is fine-grained. Fine-grained igneous rocks, those are microscopic crystals. The crystals are too small to see with the naked eye, like in this example right here. And so fine-grained rocks typically form up on the surface, and coarse-grained rocks form deep inside. Cellular is another texture, and cellular igneous rocks are the ones with gas bubbles, with the holes left inside the rocks. Hence the name, I suppose, cellular. Those are rock textures. The other 2 vocab words are right here. Intrusive igneous rocks are igneous rocks that form deep inside the earth, hence the name intrusive. And of course, they'll be coarse-grained. The other kind of igneous rock is extrusive, where the igneous rock form near or more likely on the surface, kind of like exterior extrusive. And those typically tend to have fine-grained textures. So those are your vocab words and your laws for igneous rocks. That's a lot to throw at you, but of course we spent several days kind of processing and absorbing that. So on to sedimentary rocks, and we learned many different things about sedimentary rocks when we were doing our labs there. We have some sedimentary laws. Sedimentary rocks are leftovers. They're made up of fragments of other rocks. Sedimentary rocks form in watery conditions where sediments can get eroded and transported and deposited, and that happens best when you have water around. Large pebbles in sedimentary rocks typically mean fast-moving water. Small pebbles in sedimentary rocks typically mean slow-moving water. And fast-moving water is typically shallow, and slow-moving water is typically deeper. So you can, kind of like with the crystals in igneous rocks, you can infer and interpret some things from sedimentary rocks. Seeing the size of the pebbles can tell you all sorts of things about how fast the water was moving and how deep it was. So we have some vocab words for sedimentary rocks. We've got, for example, clastic sedimentary rocks. Those are your classic sedimentary rocks, rocks that form from sediments being eroded and transported, deposited, glued together by other minerals. And I think this is the best analogy for it, or metaphor right here. It's kind of like Rice Krispie treats, or in this case, I think they're Lucky Charms treats. And they're typical, you have fragments of things all glued together. And we talked about how the minerals that glue sedimentary rocks together are really minerals that were dissolved in the water in between the sand grains, and as the water evaporates, it leaves the minerals behind, and the minerals act as glue. We saw some little animations on that. You can also have organic sedimentary rocks, and those rocks form from mostly dead organic material, like coal, for example, where it's made entirely out of plant material. Or if you remember from identifying sedimentary rocks, coquina, which is just pure shells, or even limestone, which is quite a bit of shells with just a little bit of mud. The third kind of sedimentary rock is a chemical sedimentary rock. And those are rocks formed by water evaporating and leaving behind the dissolved minerals. So rock salt is a great example of that. And yeah, we get salt that way, by evaporating seawater and collecting the salt that's left behind. Pretty amazing. Now, there are just 2 other processes or words that are important vocab words. There's erosion, so that's the physical and chemical destruction of rocks into smaller and smaller pieces. And we probably all learned that in elementary school. Then there's, of course, deposition, which is the depositing or dumping of sediments from one area to another. And you need both processes, really, for sedimentary rocks to form. So again, I'm really zipping through the vocab words. And of course, we're doing concrete spellings for these vocab words. If you remember in class, we did them for the igneous rocks as well. So I'm going to jump ahead to the metamorphic rocks so we can still get a chance to do question B3. So continuing on with B2, we have the rock types, metamorphic rocks. So with metamorphic rocks, there are some basic metamorphic rock laws. You can see 5 of them right here. As we learned from our labs, metamorphic rocks are altered been altered from pre-existing rocks, they can be changed physically, bent, twisted, deformed, forced into layers. But they can also be changed chemically. The minerals can change, kind of like fossils have been chemically changed. So you can have a whole new series of crystals in a metamorphic rock that are totally different from the original rock that it started with. These form under high pressure, intense heat, and also water is another critical piece that's needed for this change. And something we learned is that the thicker layers indicate to us more intense change, and thinner layers indicate less intense change. So you can make some inferences from there too. Now, metamorphic vocabulary. I think there are only 4 vocab words. There's contact metamorphism, which is metamorphic rocks triggered by traditionally heat from nearby magma. So if you have this magma chamber and it's touching the surrounding rock, then the surrounding rock can be changed, metamorphosed, and turned into a contact metamorphic rock, as you can see in that picture right there. The other kind of metamorphic rock would be the regional kind, regional metamorphism. And those are metamorphic rocks triggered mostly by pressure from large parts of the crust crushing together. And you'll learn certainly more about that when we get to plate tectonics. But you can see a little diagram of what that pressure can be like, forcing the rocks to compress, even bend and fold a little bit. The best analogy or metaphor would be something like this, where you have a crusher crushing cars and squishing them and compressing them, and all the heat that's generated from that pressure. And the equivalent of that in nature would be something like this photograph right here, where you can clearly see some sedimentary rock layers that then get massively bent and warped and put under high amounts of pressure. I would speculate that you'll find some metamorphic rocks at the heart of this, because there was a great deal of pressure going on to deform those. Then the last 2 vocab words when it comes to metamorphic rocks, you have foliated and non-foliated. Foliated metamorphic rocks are rocks with layers, and non-foliated metamorphic rocks are without layers. And you can see this is a foliated metamorphic rock with layers, and this is a non-foliated. If you recall from our labs, the reason some rocks are non-foliated is because you simply only have one material, one mineral to work with. And in a case like this, you can only get 1 layer out of one material. It's just what you have to work with. So non-foliated and foliated metamorphic rocks. And that leads us then finally to finish off B2. So B2 is the big one. You've got metamorphic rocks, you've got igneous rocks, you've got sedimentary rocks, all in there with all their vocab words. And they are quite different from each other, which I suppose is part of the point. For the last minute or so, I'd like to wrap up and talk to you a little bit about cross-cutting relationships. There was a worksheet that we did that you can see right here. It's in 2 pages. And the idea is that you take what you know about metamorphic rocks, sedimentary rocks, igneous rocks, and you combine it together to make interpretations. This is question B3, which is what kind of observations can you make to really know how a rock formed. And you've got lots of clues right here. We have all these sedimentary layers, I and J and K and layer L and M and N. And you can see how they've all been warped and bent and folded. So they've been put under pressure. You can also see some other things. You can see a fault line through here at D, which has cut off the rock. And you can see that there's been some erosion here at B. And you can also tell that some more layers formed on top after that erosion happened at B. We have layers O and P and Q. And you can even see this rock right here, which looks to be an igneous rock, R and C, melted through. And you see how R and C cut across all of the other layers. And that's really what this is about, cross-cutting relationships. And when you can see that some rocks cut across others, you can establish an age. R and C have to be among the youngest rocks because all the rest of these rocks had to exist in order for this rock to come through and melt through all of the others. Probably the oldest rock is I. The sequence probably was I, J, K, L, M, and then N. And then you had erosion at B. Then you had O, P, and Q form on top of that. And during that time, you would have had this fault happening at D, and you would have had this igneous intrusion at C and R. It's a lot to take in all at once, and so, take it a little bit slowly here. The worksheet here on the back page, you have this picture right here, and again, it should show you the cross-cutting relationships. You can see that D and E formed first, then they had the fault, and then A came in and melted through here. Then there was this erosion. B happened first, then we had the erosion, then F and G and H formed, and then C formed last. So that's it in a nutshell for B3. You can use your cross-cutting relationship worksheet to actually throw in there as notes once you complete the sheet. and autocorrect it. So that's big idea B, trying to figure out how rocks talk to us and what it is they're trying to tell us exactly. They're kind of like pages in a history book. So that was a long one, almost 15 minutes long. You endured. Well done, folks. Maybe I'll see you around for big idea C.